welcome to Straight Science. This is an evening science presentation put on by UAF Northwest Campus in Nome and UAF Alaska Sea Grant. And this, like I say, this is the home office these days. So tonight we've got, I'm very excited. I'm excited to meet Harper Simmons, but also to see Jim Thomson and Jennifer MacKinnon return to Straight Science because they've been Straight Science speakers in the past. And they've got a story that's directly affecting us here or I guess we're almost, it's not really well, it is affecting us, but it's also happening in our backyard. It's what we're sending north, as we know in this region, how things flow. So their work on the UAF vessel Sikuliaq over the years have brought this about. And I think it's going to probably be I know it'll be very interesting, but it'll probably end up not being the best of news if you want to see sea ice melting at a slower rate than what we've been experiencing. But it will explain quite a bit maybe of what we've seen. So Jennifer MacKinnon is a physical oceanographer from Scripps University, and she is zooming in tonight from San Diego, California. And then we've got Jim Thomson. He's with the University of Washington, also a physical oceanographer, and he is calling in from Seattle. And we've got Harper Simmons, Alaska's own, a friend or colleague of Seth Danielson, who is a Straight Science favorite. And he is calling in from Fairbanks. So I'm excited to bring you all to introduce you to Nome and the Bering Strait region. And with that, take it away.
All right, I think Harper was going to start us out.
Yeah, I just wanted to start with a land and waters acknowledgement. So first, I'll acknowledge the Sikuliaq. That's first, but more importantly, I would like to make the land acknowledgement. And so we acknowledge the First Nations upon whose ancestral lands our various campuses reside. In Fairbanks, our Trothieta campus is located on the ancestral lands of the Dana people of the lower Tanana River. And we also recognize that we conduct our research on the traditional subsistence hunting grounds of the Yupik and Inupiat peoples. We thank them for their continued stewardship of these waters. With that, I think Jen is going to start with the first part, and then I'll come in the middle, and I think Jim will come in towards the end. We're doing this with three speakers tonight.
Thank you, Harper, for that acknowledgement, and thanks for the opportunity to be here. It's always I've really appreciated opportunities to go to Nome in person, and now it's nice to do so virtually and really see people. So the work we're going to talk about today took place on the Sikuliaq, as you can see here, and it included quite a range of co-authors, including Seth Danielson, who is here on the call, as well as a fair number of our other colleagues. So to start off this work, I'm going to start with something that is probably not news to anybody on this call, which is the accelerating rate of sea ice loss. And these are a couple pictures. This is from one of the recent IPCC reports. And they show the trend, the changes in both sea surface temperature and sea ice in March and in September. And in particular, we are interested in this region, which is your backyard, which is the southern Beaufort, whereas you can see in this pink square here that sea ice rates, the loss of sea ice has been particularly dramatic compared to even the rest of the Arctic. And so one of our goals is to help understand why that sea ice is declining so quickly, more quickly than many of the climate models predict, which doesn't mean that we can stop it, but at least we can kind of help understand what's happening and make accurate forecasts so that people can predict and plan. So the gist of what we're doing or how we're trying to understand the accelerating sea ice loss really revolves around understanding the structure of the Arctic. And the Arctic for those of us who also work in other oceans, has a very special structure. So most oceans in the world are stratified by temperature, meaning they're warm on the top and cold on the bottom. You know, like hot air balloons, the warm water goes up and the cold water sinks because it's dense. And so the Arctic is a little bit different in that what primarily determines how dense the water is not the temperature, but the salinity, how fresh it is or how salty it is. And so these plots on the left are just profiles. If you dropped a sensor down in the ocean and you looked at how the temperature of the water and the salinity of the water, how salty it is as you go down. And you can see that it gets saltier and saltier. It's very fresh near the surface, and there's that's due partly to rivers and partly to ice melt in the summer. But it gets saltier and saltier as you go down, and hence denser. But because the density is not determined by temperature, you can get these pockets of warmer water below the surface that's denser than the surface water because it's saltier, even though the warm part normally would make it lighter. And so if you look at the spatial structure of that, this is what this schematic on the right shows us. This is kind of going all the way across the Arctic. There's water near the surface, which is really cold and fresh, but then there are these pockets of warm water below, and we think these pockets are supplying some of the heat, which is making the sea ice melt more rapidly. So some of this warm water comes in from the Pacific. It comes through Bering Strait and enters the Arctic, crosses the Chukchi and enters the Arctic there. Some of it comes from the Atlantic Ocean on the other side, and you can find some of the Atlantic water all the way over in the Beaufort as well, although it's pretty deep over on this side of the Arctic. So understanding these, how these pockets of warm water get there and how they're changing is an important part of understanding the accelerating sea ice melt. And just as a reference, in sort of more technical units, the net heat imbalance between heat coming in from the atmosphere and heat going out of the ocean is only, the units are 1 watt per meter squared. So per square meter of the ocean surface, only the difference averaged over a year of plus or minus a watt of total heating can be enough to make the ice melt or not. Melt faster, you know, accumulate ice or lose ice on average. So these are small differences. So to see how that layer, the subsurface layer, is changing. So one of our colleagues, Mary Louise Timmerman, who's a professor at Yale, and some of her co-authors have been looking at how this subsurface warm water mass is changing. And so she's made these plots here, which show from 1987 to 2017, this is this subsurface layer of warmer but saltier water. And you can see a couple decades ago, it only occupied this area real near the coast, but over the last 20 years, it's been spreading out and warming. So there's a growing pool of heat, like lurking below the surface. If we try to compare that, here's that picture again of sea ice, the rate at which sea ice is melting. You can see that the pattern of where this subsurface pocket of heat is growing looks similar to the map of where sea ice is melting most rapidly, which tells us that they're probably connected, that the subsurface water may be supplying the heat. So it's that's accelerating the sea ice melt. And one more thing that kind of makes that case is this picture here. So these folks looked at the sea ice melt in this region and tried to guess whether the ice was melting due to heat from above because the air was warming, or whether it was melting from the ocean melting it from below. And so over here in the Western Arctic, the yellow bars are how much of the heat is coming from the ocean warming below. And so that's at least as much, if not more in some cases, than warming air above. So these pockets of heat in the ocean are playing an important role in melting the sea ice. And so we're trying, again, to understand how they get there and how they're getting warmer.
Jennifer, this is Gay. Just a quick question for your graphic on the upper left. Can you just walk through maybe a little bit what that's showing?
Sure, that's the same one as the previous slide. So these are profiles. So this is if you dropped a sensor that was measuring temperature and salinity, if you dropped it from the top of the ocean to the bottom. This is, so on the right, you see the salinity that you would measure. So this line is getting, it's the salinity, the units we use are kind of parts per thousand of salt. So it's 25, which is pretty low number. This is water that's fairly fresh near the surface. And then as you get deeper, it gets saltier and saltier and saltier. So it's getting denser. The one on the left is temperature. So as you go from the surface, it's cold, but there are these pockets of warm water that are warm water, but they're saltier. So they're sitting below the surface, and it's this reservoir of heat that is being made available to melt the sea ice from below. So what we're trying to understand is how this heat got there, how this warm water gets there subsurface.
Terrific. Thank you so much.
Oh, my pleasure. So here's just, I guess, a summary again of those points, that in the southern Beaufort, there's a layer of warm salty water below the surface. This subsurface pocket of water is getting warmer and warmer, and it has a similar pattern to the areas where the sea ice is melting. The warming atmosphere isn't enough to explain the sea ice melt, so we think the heat is coming from the ocean below. And we know this warm water comes from the Pacific. It's called Pacific summer water. It tends to arrive in the summer, and it comes from the Pacific Ocean through Bering Strait across the Chukchi. But how exactly it gets from there into this, layer within the Beaufort is the mystery that we're trying to figure out with this work. And so we know a few clues to that mystery to start out the work that we did. And so you can see a little bit of that in these plots. So the plot on the left, this is a picture of this sea surface temperature from satellite. And these arrows are different suggested pathways that water takes. And so the water we're interested in is this water, the Alaska coastal water that follows the coast of Alaska. It's the warmest water, comes by Nome, comes all along the coast, and then it pours through Barrow Canyon. And so this one on the upper right is a slice through Barrow Canyon if you measured the temperature of the water. So this is depth, if you were able to kind of take a snapshot of the temperature in the Barrow Canyon, the depth, and then this is sort of the distance across Barrow Canyon. And so on the right side of Barrow Canyon, you can see banked up against the right side. So this is water that's flowing into the page, gushing down Barrow Canyon. It's really warm. It's 6, 7, 8 degrees Celsius, which is well above the freezing temperature. This warm water is gushing down Barrow Canyon. And the plot on the bottom is telling us, this is a similar plot, but this is looking in time. So this is depth axis, and these are different years. So 2002, 2003, and that shows us from July to August, September, November, December, these pulses of really warm water, which are pouring, gushing down Barrow Canyon. And so this has been happening for a while, last decade or two, that the super warm water is gushing down Barrow Canyon, particularly in August and September. And so the question is, we're trying to connect this warm water gushing down Barrow Canyon to this layer that we see throughout the Beaufort and trying to understand how it gets there. So here's one more recapitulation of a similar thing. This is again a sort of schematic. So we're looking at this warm water that comes along the Alaska coastal current. It pours out of Barrow Canyon. Does it go left? Does it go right? Does it go straight? How does it turn to this, growing red lurking blob of heat that we know is there throughout the Beaufort? So we had an opportunity, I'm just going to show a couple more here and then pass it off to Harper. We had an opportunity to really closely observe one of the events, what happens when this water gushes out of Barrow Canyon and then how it enters the main Beaufort Gyre. And I think it's provided us some really useful clues as to how this process works and how this water is getting into the Beaufort and how that may evolve in the future. And so here's a picture. This is another image from a satellite from space showing temperature of the ocean surface. And here comes this warm water gushing down Barrow Canyon, and you can see this warm jet. This is 6, 7, 8 degree more water. It's very warm, and it shoots straight offshore, and it does a bunch of slow meanders, like a meandering river. It kind of jets out, if you imagine coming out of a hose, and then it sort of meanders around a little bit. And if you look at the meandering, you can see it's really warm when it first jets out of Barrow Canyon, and then it gets a little bit cooler as it goes along. The colors are getting less red. The redder colors are warm, and then it's getting less cooler as it goes down. And so this is the picture of the surface. So we think that warm water is diving beneath the ocean surface here. we can combine this. This is another type of satellite. This is a satellite looking at how rough the ocean surface is. And you can see it. You can see the signatures of this roughness. Here's the same jet coming out. But in this type of picture, you can see different information. You can see this jet coming out, and this is a remnant patch of ice that was around in this area in mid-September. This is mid-September 2018, and you can see this warm jet is plowing, making this sort of mushrooming pattern, plowing straight into this pocket of ice. And you can put them together, and here's a combined version that's just smoothed a little bit, where you can see this meandering jet plowing into the ice. And I think now I'm going to turn it over to Harper to start to help us imagine what happens to features like this after they gush out of Barrow Canyon.
All right, awesome. And this is Gay, and so we'll hold questions until the end, I guess, unless there's some burning thing. And then you can go, and we'll either use the chat function at the end, which is on the bottom of your bar, looks like a little cartoon chat bubble and says the word chat. And if you click on that, if you're unfamiliar with Zoom, you'll get a text, and you can start to write questions, which we'll get to afterwards, or you'll be able to ask questions directly. So thank you. And
yeah, so
oh, go ahead, Jennifer.
No, I'm just saying, okay, yeah, nothing.
Okay.
Take it away, Harper.
Yeah, so Jen, could you go on to the next slide? Okay, great. Yeah, so go ahead and let this run, and I'll start to help people understand what they're looking at. I'm happy to have people interject with questions. That's absolutely fine with me. This is a informal situation. What you're seeing here is a simulation of the ocean circulation in this area, and actually, yeah. So let's just pause it here. So the observations that we made were in part satellite measurements, and they were also measurements that were made from the ship. And both of those ways of looking at the ocean give us a very complicated and difficult to understand view of what we're seeing. And so one of the values of these simulations, and think of these simulations being something like the ocean equivalent of a weather forecast model. Although in my case, I would say that these simulations probably have less predictive ability than an average weather forecast model, for a variety of reasons, one not the least of which is that we don't have nearly as much data to constrain these simulations. But they do allow us to kind of see how rapidly things are evolving and how complicated these warm structures that you're going to see are. So Jen, if you would start this over from the beginning. This is a 1-month simulation, and the panel on the left is the warm, you can see the warm water streaming in through Barrow Canyon. And then what you see is that it, throughout the month, it starts to break down into these extremely complicated filaments and whorls. Jen, do you want to stop it for a moment? Yeah, so actually this looks like this is the end of it. And I'm a little bit concerned, so, you know, these animations don't necessarily work extremely well if you don't have really fast internet. So I'm hoping that people can make sense of this. And I can send around this movie later if people want to look at it. Yeah.
I'll jump in for just a second, and that is, so what we're looking at then is the red is warm water coming up from the Bering Strait region, and the landmass you're showing us is the North Slope. So the tip of that is Utqiagvik with Barrow.
This is Point Barrow. Utqiagvik is just a little bit down from there. Okay. And you know, Wainwright and all that down here. So this is Barrow Canyon here. And this is the Chukchi and the Beaufort.
But this is the red is the water we're sending north.
Correct.
Going past Diomede. Okay. Awesome. Thank you. I just
Yeah,
wanted to.
yeah, and you know, this is a tool that we use to kind of understand these measurements in a different way. They're, as I said, they're not meant to be perfect predictions. It turns out that's essentially an impossible thing to do. But we can look at these simulations as little. Think of them as computer simulation laboratories that allow us to, you know, among other things, appreciate just how complicated these structures are in space and time. Uh, yeah, so this is yeah, so this is a simulation which is meant to be a you know, a after the fact visualization of what we saw in September 2018. But as I said, it won't match the observations exactly, although hopefully the structures have some similarities to what we see. So Jen, do you want to go on to the next slide? With that simulation for context, we're going to now tell you a bit about the way we observed this very warm water from the Sikuliaq using a variety of instruments. I see that our dean was getting seasick. Sorry about that, Brad. This probably doesn't help. Although this was a pretty nice, we had pretty nice weather, actually. This was unusually nice weather in September 2018. So there's a suite of instruments you can see here. In the upper left is one version of the workhorse oceanographic instrument that almost everyone uses, which is, we call this a CTD. It allows us to measure temperature and salinity versus depth in the ocean. This is a very specialized version of a fast CTD, which is called a fast CTD, and it allowed us to measure the thermal and salinity structures in really, really unusual detail. In addition to this, we had other instruments which were put over the side of the boat and were able to sample away from the boat, and then were recovered at the end of the cruise. So in the middle, you're looking at something called a wire walker. It's a drifting instrument that profiles up and down, making measurements. There's a wave glider, and I believe that is Jim Thomson, I think, over the side, manning it. And
It's me.
yep. And then on the right, these instruments called swift drifters are some more instruments that Jim brought on board for this cruise. So this was all in support of an experiment called the Stratified Ocean Dynamics of the Arctic, or SODA. And again, most of what you'll see was from September 2018 on board the Sikuliaq. Next slide, Jen. So again, this is up at the top is the satellite view of the ocean that we were able to acquire in the middle of September of that month. It's very unusual to get a view like this. We often don't have clear skies that allow us to measure the surface temperature in this kind of detail from space, but we had a few clear days and were able to get this really remarkable view. And then below, this very complicated looking bit of temperature, you can see that it's using the same color map that you're seeing in the satellite image, meaning the really red colors are maybe 6 degrees, 6 to 8 degrees above the freezing point. And then the dark blue colors are about the freezing point of seawater. Oh, I see there's a legend there on the lower left. And in the middle, you can see some black lines that are drawn on the satellite map. Those correspond to these sections where we were measuring temperature along the way with the fast CTD system. And the important thing here is that if you look at these sections, actually, the warmest water is not at the surface. There's warm water at the surface near Point Barrow and in Barrow Canyon, but offshore, as you reach the remnant sea ice pack, all of the warmest water is actually hidden from view from the satellite and is below the surface. And so in these, there's these big, really quite angry looking blobs of very warm water that are sort of typically between, you know, a few tens of meters below the surface down to 100 meters below the surface, in these big pockets of warm water that somehow managed to get from the surface in Barrow Canyon and through a process that we call subduction, slide into the ocean interior and start to populate this warm interior water that you actually can't see from the surface once you get offshore. Next slide. And I think I'm going to hand it back to Jen here at this point, because she is really good at explaining this, and I'm sure we'll do a better job than I will.
So this is kind of the final part of this story. Thank you, Harper, for that opportunity. Which is, so this is now, these plots here are looking at a slice. If you look, you know, there's that meandering river that you could see on the surface of the ocean, and this is what it looks like beneath the surface. So these plots, again, the color here is temperature versus depth, and sort of along a slice across this river. And on the left side of here, this is kind of the water that's coming out, you know, gushing out of Barrow Canyon. It's warm from the surface down to 100 meters. And you can see it's tapering in this wedge. And we think what's happening here is that as this water is coming out, it's being squeezed, and we can actually calculate by looking at some features of how this jet is meandering around, how this water, and it's sort of schematically shown with these arrows down here. This is the same picture just blown up with little arrows on it, that this water is being squeezed into this wedge. So it's being squeezed down from the surface into this little triangle. And then something really interesting happens to it. So as it's being meandering around, it's being squished down below the surface. It's just like an ice skater. So as it squishes, it starts to spin. And it's conserving a type of angular momentum, just like an ice skater who gets taller and then shorter and sort of spins at a different rate. So as this water is squished, it starts to spin in order to conserve its angular momentum. And it turns into these spinning little eddies, spinning little blobs. And these are some of these things that we're calling heat bombs. They're little spinning blobs, and you can see them, they're starting to spin and they're starting to break off. So here's it's kind of uniform, the river gushing out, and it's starting to turn into these little blobs that are going to spin off into the distance. And so it's been a fun, complicated physical process to try to understand, but we think this is how the water is getting out and then shoved under this layer under the surface of the main Beaufort. I can just say, we just have a couple more on this part of the talk. So in addition to bringing heat, this water from the Pacific, so this water is coming through Bering Strait, gushing down Barrow Canyon, spinning out into the central Beaufort, and then squishing itself into these little subsurface blobs or heat bombs. But in addition to carrying heat, they're also carrying unique properties in terms of nutrients that affect the Arctic ecosystem and are probably changing the Arctic ecosystem. So we had a really nice collaboration with some colleagues from the UK, and they were looking in detail at water samples, and Seth Danielson, who's here, was also part of this work, trying to look at the different components that were in this water mass in terms of the different nutrients that provide the food for the ecosystem, kind of from the really small level, phytoplankton level, all the way up. And so just looking at the top part here, these are some more plots, little slices through this warm jet. And so the color is temperature in this one, depth, and sort of a slice through the jet. And you can see where these little blobs, these warm little heat bombs of warm water, they also, you can compare the temperature and then look at this third plot here. So this is dissolved organic material. This is biological stuff that's coming off the coast. And you can see this is coastal water, which is bringing a lot of coastal biological material with it as it's being ejected into the central Beaufort. So this is changing the Arctic ecosystem as well in ways that we do not fully understand. So consequences for heat, consequences for that. So we think some of these little heat bombs coming in can swirl around under the surface for months or even years. They're diffusing their heat upwards, but it's diffusing upwards pretty slowly. And so that allows them to get pretty far under the main ice pack and melt it from below. So an obvious question is this phenomenon that we saw a freaky, weird event that happened that one time, or is this something that's happening frequently, that happens increasingly often maybe? And it seems unfortunately like it's the second option. And so these are some pictures from other people's papers. These are also views of the surface of temperature. And you can see there's actually a number of these occurrences where you see this warm water gushing out of Barrow Canyon and then turning into these meandering features and filaments and jets and things. And we think this water, similar things is happening. It's meandering around and then diving down beneath the surface and spreading out. So it seems like this is something which is happening more frequently and pumping this water below the surface. And then finally, before we turn it over to Jim, who's going to talk about some of the related impacts of melting sea ice much closer to shore, we have this one little movie, which I will show. It's a summary.
Feel free, Jennifer, to sort of describe what we're looking at as we're reading.
Okay, so this, can you see the text as well?
Yeah.
Yep. So this is, so here's, here's the melting seawater on the surface. So this is a little animation of what we thought of what we saw. This cartoon, here's water gushing out of Barrow Canyon. This is what we saw in our data, that it's gushing out and then it's diving below the surface in this triangle tongue of warm water. It has unique biochemical properties that it's bringing with it. And then as it dives down, it's squishing and these little blobs start to spin around. There they are. They're starting to spin around. Our little heat bombs. And here, so here they are. Once they get subsurface and start to spin, they spin themselves further north. And so they can go pretty far and get under year-round ice and slowly melt it from below. These are some of the instruments that Harper described, which are measuring the temperature, salinity, ocean currents. So there's a lot of technical achievements as well as science insights required to do some of this work. And there's Harper. Rain or shine. So again, this work is designed to try to help us understand so that we can make more accurate forecasts of these processes, which will help people plan. Okay, and with that, I'm going to turn it over to Jim, who's going to talk about what's happening closer to the coast.
Thanks, Jennifer, and bring us home, Jim.
Okay. Of course, we should ask, since it's kind of an intermission here, does anyone have questions that are related to the stuff we just saw while it's fresh in your minds? Well, then I guess that's a no.
We do have a question in the chat box if you want to take it, or if you want to forge on. It says, how frequent? Any thoughts about 2019?
Well, it seems that measurements from 2019 and 2020 indicate that the at least 20-year-long warming trend that people have been noting, or longer, really, but there's been a pretty marked warming trend in the northward flowing water that's continued through 2019 and 2020. And I don't know what's been measured in the 2021 season, but certainly the last few years since we were out have continued to be warmer and warmer.
And thank you. And you've got a question in the chat box, and I see you, Dean, too. The chat box question is, I was wondering about what is causing the pressure on the top and bottom of the heat plume, making it go into a triangle. In other words, why is it being squeezed into a lens as opposed to staying as a taller layer?
I can try this one. So there's two parts to the answer. One is that the water which is coming out has a particular density. And so it's, because it's salty, it's denser than the water that's on the very surface of the Arctic above that wedge, but it's less dense than the water that's colder and saltier below it. And so it's being squeezed into a layer which is appropriate for its density. It's like, the three bears. It's not too warm, not too cold. It's just in the middle, just right. So that's why it goes into that layer. Why it's being squeezed has to do with the fact, as the jet meanders around, it meanders, and there's parts of that meandering that make it squish sideways, and the squishing sideways makes it spurt below. And there's a more technical part that isn't the squishing and spurting, but it's essentially that. It's the meanders squish it, and so it goes into its density layer which is where it belongs.
So it might help, and maybe I have this wrong, so correct me, any of you guys, correct me. But here in the spring, we get a lot of melt. And so you can have fresh water, a more fresher water on top during the spring here
100%.
when the ice is melting anywhere, but I'm just talking about right here.
Yeah.
And sometimes if you are harvesting something like a seal and it sinks, sometimes you can see that it's just laying about 4 feet below.
Huh.
It's just laying there because the warm water coming underneath is, the salinity is different, and so
Yeah.
the animal just falls to
Wow.
a place that it can float.
That
And so
is-
that
yeah.
is that what it
That is
sounds like, what you're describing, that the fresh water is on top from the ice melt, and that the Bering Strait water that's just coming underneath. And so you'll see those kind of things here where things will get stuck. Is that what we're talking about?
That is exactly what we're talking about. And that is I have a whole new way to think about it and explain this. Thank you. That is perfect.
So then you just use your, to retrieve it, you can grab it or harpoon, that sort of thing.
Yeah.
You'll see that very occasionally.
Yeah. No, that's amazing, actually.
That was outstanding. Jen has a new analogy. I see that Dean Stockwell has raised his hand.
Yep, Dean's been very patient. Go ahead, Dean.
Really nice talk. I like seeing this the way you put it in perspective, but I'd like to kind of put the whole heating of the Arctic into perspective. You have heating not only from the Pacific, but from the Atlantic. Can you give me an idea of the relative proportion of heat influx? Because I know the Kara and Laptev have seen a big reduction in their ice content, and that's coming up from the Atlantic. And a second A second question I have has to do, I guess, with 2020's big Siberian heat event where you had 38-degree temperatures up off the Siberian coast, putting all that warm water coming down the East Siberian Sea. That had to have a big impact on that ice field. And I just
38 degrees
thoughts on
Celsius.
that.
Yeah, that is true. I do not know what happened after that event, which I remember hearing about. There is a ton of water coming in through the Atlantic as well, which has a huge impact. Very, very similar processes happening on the Atlantic side, that the warm water comes in and kind of dives beneath the surface there and swirls around. I don't want to say the wrong numbers unless Harper or Jim knows off the top of my head how much heat is coming in one side versus the other. But I will say on this side of the Arctic, there is Atlantic water, but it's really deep and it doesn't affect the sea ice much on this side of the Arctic. And so
Right, that's sitting about 400 meters. I'm aware of
So
that. I was just trying to get an idea of the difference in flux.
That's
Is it bigger in the Atlantic or bigger in the
yes,
Pacific?
no, it's bigger in the Atlantic. I
Okay.
think I'm going to say roughly that the Pacific water is something like a third of the heat flux or something. It's a fraction, but not a super small one.
Okay. And a comment then on your productivity group showing nutrients and things coming up. If you go way back to studies done in 2000 looking at that, you'll see that a lot of the nutrient rich water is moving through that area about at the same depth. I don't know if the concentrations have changed, but that depth of 30 to 40 meters is where everything is really still rich in nutrients. And I noticed that your chlorophyll numbers in that area, there's usually a subsurface chlorophyll max, and that's historical, but that's another story. But great stuff. I like saying this. Appreciate it.
Oh, thank you.
Yep.
Okay, Jim, why don't you go ahead? I want to get to Jim's
Yeah,
slide.
Jim's waiting in the wings.
Okay. Well, so I want to take the heat story to the coast. This story was all about the heat that's coming in and going past Nome and then around the corner. And one of the follow-on consequences of that is that there's a lot of erosion happening at the coastlines along the North Slope. And I'm sorry this graphic doesn't include Nome. I know Nome has its own coastal change happening and erosion happening, and it's definitely a hot topic throughout Alaska, really, and throughout much of the world. This was a follow-on project where we focused on the North Slope. So apologies for the geographic bias. And in the color scale here is the rate of shoreline retreat per year. So that's a horizontal number, how far the shoreline marches backwards per year. And the red numbers are negative, that's going backwards. And you can see it's almost red everywhere. So there's about 2 meters per year of shoreline that are lost along the North Slope. This is a database that's maintained by the USGS. This is not something we've put together. It's a long-term data set that they've been working on. And 2 meters per year is significant. I mean, if you're, if you have a coastal road, that could take out the road in under a decade. And those kind of things have been happening. So I think everyone's well aware of this, and there are a number of factors that are contributing to this. But one of the biggest ones is just that there's less ice, and there's less ice because there's more heat. Another compounding issue is that as there's less ice, there are more surface waves. And that's something that I've talked about quite a bit in prior straight science presentations. And the overall idea is quite simple. If there's less ice, there's more open water. And when there's more open water, we call that fetch. There's more room, there's more space for the wind to do its work, for the wind to build up waves, and the waves can get quite a bit bigger, and they can carry a lot more energy into the coast, and then they can drive more erosion. So it's really a multi-part story with more heat and less ice, bigger waves, and more erosion along the coast. So this follow-on project that we've had in 2019, 2020 to take some of these similar kind of measurements closer to the coast, I want to give you some preliminary results from that work. So next slide, please. So we have been measuring at 3 focus sites, and in the upper right panel, they're shown. They're at Icy Cape, they're at the Jones Island, and they're at Flaxman Island. So again, all north of Nome, apologies. But in each case, we have a measurement that's close to shore, which we think of as really indicative for where where the conditions that drive coastal change and coastal erosion are happening. And then we have a measurement further offshore. And the purpose of having that measurement further offshore is to kind of understand where the signal is coming from, where the forcing is coming from. But it's also to understand how things relate to the global climate models, because a lot of what we can say about the future relies on these global climate models. And these models are big. They're running across the entire globe. And so their resolution isn't that great. And they don't do a wonderful job of resolving what happens near the coast. Even though what happens near the coast is very important to a lot of us who live there, the models they're not designed to do that. They're designed to give us the big picture signal of what's happening regionally. And so part of what we're trying to do is make that connection between these long range global forecasts for climate change that are quite coarse in how they resolve things. We're trying to make the connection to that and what actually happens at the coastlines that people live at. That, again, turns out to be tricky sometimes because the big climate models aren't designed to do that. So the panel on the left is a time series of the waves that were measured for 1 year at Icy Cape. And the wave heights are in meters. That's the vertical axis. So 1, 2, 3 meters, that's up to about 10 feet. It's about as big as the waves we measure there. We measure a whole annual cycle. So we put things out in fall 2019. We get waves for a couple months. Then the sea ice comes in, and there are no waves when there's complete sea ice cover. I think everyone is well aware of that. And you live it right there, and it's in your backyard in Nome. No waves in the winter. And then the springtime comes and breakout starts to occur, or at least the melt starts to occur, and some waves start to form. And then as the summer and fall go on, the waves get even bigger. But that springtime part is particularly interesting. That's the pink shaded region there. If you look closely, you can see that there are only gray symbols there. The gray symbols are the measurements that are further offshore, and the waves are 1, 2 meters pretty regularly. There's different events, different storms comes through. They last a few days to a week, and then they calm down, and it comes again. There are no light blue or teal colors in there. That's because the inshore station hasn't measured any waves yet, and it doesn't measure any waves until July. And the reason it doesn't do that is because there's still shore fast ice at that location. And indeed, as I'm sure you're familiar, there's shore fast ice along the whole coast that's fairly persistent in the late spring and early summer. And the rest of the pack ice can go away, and the shore fast ice will stick around. It's often grounded, it's much thicker, it's been compacted along the coast for the whole winter, and it can stay around for a while. Now, it varies year to year, and occasionally it breaks out in a spectacular event that happens all at once. But in general, the shore fast ice sticks around. And so one of our key measurements is something that's quite obvious. That shore fast ice protects the coast. It keeps the waves from penetrating all the way to the coast. If you look at the bottom right, this is a sea ice product from some satellites that shows us exactly that this shore fast ice is present, and that helps us interpret the data. So in that, we're looking at the North Slope, and the blue is open water and the white is ice cover. And you can see our little measurement stations there, and you can see in your Icy Cape, there's some ice left by the coast. And you can see over at Jones Island, the Flaxman Islands, at this particular snapshot in time, this is mid-June, those have started to open up also, and they're opening up offshore before they open up onshore. So kind of an obvious thing that the shore fast ice protects the coast, but our question is how much, right? We want to be able to quantify that. We want to be able to make the connection back to these global forecast models that are telling us, hey, what's going to happen 10 years from now, 50 years from now, 100 years from now. Those predictions are not really tuned up to give us an answer at the coast, and we want to make that link. So that's a long, detailed description of what's happening at Icy Cape. I can show you quickly what happened at the other two sites. They're pretty similar is really what you need to know. There's also shore fast ice, and it protects there. And that's those pink regions which last a month, 2 months, depends on the site, where there are strong waves measured offshore because there's open water offshore, but inshore, the shore fast ice is still present. It's very persistent, and it protects the coast. And it protects the coast in two ways. I should pause and remark that it's not just that the ice is protecting the coast from the mechanical action of waves coming in and stirring up the sediments and clawing at the coast, but there's also a thermodynamic aspect here. There's again, temperature is really where the whole story starts and ends. That much of the coastlines that are eroding because the permafrost is melting, and that's about the water temperature. But when the sea ice is present, the sea ice holds the seawater near the freezing point. So if the shorefast ice is still there, then you have double protection. Basically, you have the shorefast ice stopping the waves, and you also have the shorefast ice holding the temperatures nice and cool, so the permafrost that's at the coast won't melt away. Once the shorefast ice is gone, then you have usually the worst of both worlds. You have waves that are coming in and impinging on the coast, and you have warm water. And in fact, the waves are carrying that warm water further up the beach and up into the nearshore bluffs or whatever the foreshore is, and carrying that warm water up to a location where it can melt the permafrost. So then it becomes sort of a worst case scenario pretty quickly after that. Anyway, back to the idea that our data helps us make the connection to the global models. What we want is this metric for what's the coastal exposure? What's driving this this coastal erosion? We have simple numbers like 2 meters per year for the coastline as it erodes. How about some simple numbers for what's the total amount of coastal wave exposure? So that's what's on the next plot. It's a cumulative amount where in time is on the x-axis, going from May in the early summer until September in the late summer. And these growing lines, this is throughout the season, the coastal wave exposure as the number of days of a certain wave height in meters. So if the number on the vertical axis there gets to about 100 at the end of the orange and gray lines, what that 100 means is that's 100 days of 1 meter waves, or it's 50 days of 2 meter waves, and so on and so forth, right? That's what that cumulative number means. And that's the number we're working with to try to have a sense of, in general, for a given year, what's the total wave exposure of a particular site at the coast? So this is a metric that we're using. We're also doing some more rigorous things that are total energy flux and things like that are, but this one I really like because it's something you can really get your head around, right? Okay, 100 days of 1 meter waves, that's what I got. And you can see there's different lines on this cumulative plot of what happens throughout the season. The orange and gray lines, those are what happens offshore. And you see really nice agreement between those two lines. Those two lines are, one is our data, those are the measurements in gray, and the other, the orange, that is one of the global forecast models. That's one of these climate models that's trying to tell us what's happening this year, next year, 100 years. And it works really well. It works great. It gets this offshore measurement quite well. What it doesn't do is have any information any closer to the coast. So that forecast knows nothing about the presence or absence of shore-fast ice. It's completely just unaware of that. It's completely naive about that. So our measurements do have that shore-fast ice effect, and that's what's shown in the teal line, or that light blue line. That's what's happening inshore. And you can see that the total coastal wave exposure is a lot less and when the shore-fast ice is there. And so this is an important difference. So the question is, how do we make that connection? So how do we fix that global forecast model without asking, the forecast centers to rerun all their models at, 10 times the resolution and at great expense, which they're not going to do. It's not going to happen, not anytime soon. There are plenty of people working on that, but it's not happening yet. Well, we've come up with a correction, and that correction gives us the kind of faint purple line. And so I'd say that correction works pretty well. Rick is commenting that AERO5 is a reanalysis model. That's a good point. Point well taken, Rick. I agree. It's still the same family of models that's running on a big global half-degree grid, and that's the resolution's the problem, I would say. It's not intended to get this coastal stuff right. I shouldn't really be criticizing it. It's doing, look at the orange and the gray lines. It's doing what it's meant to do quite well, exceptionally well. It's just not getting the coastal stuff. So we've been working on applying empirical corrections that let us, use the available information, particularly the temperature, because the temperature is what controls the ice, and using a temperature mass, be able to make an empirical correction and say, well, actually, we think the waves that are making it to the coast are that light purple kind of lavender colored line there, and it works pretty well. So our job from here on out is to try to roll this out across all of our sites and across the whole coast and end up with this coastal exposure number that we can try to start to match up with patterns of erosion. So this project's ongoing, don't have the final answers yet, but we have this nice data set, spans a whole year, shows how important this contrast between the offshore signal that's forcing things is and the nearshore signal right at the coast where things are happening. And there's a big difference there, and we need to account for that, and that's presently not being done. So that's the big takeaway for both the scientific community and also for the local communities that live there, is that, you know, some of the forecasts at the moment are, you know, or the reanalysis products, as we try to look backwards for the last 50 years and say, how did we get here? How is all this erosion happening? What's been the signal over the last 50 years? The signal has been that coastal wave exposure is increasing, the waves are getting bigger, the temperatures are getting warmer, and that's all driving coastal change and coastal erosion. But it's not happening at quite the same rate that we had thought, because we hadn't taken account this effect yet. So I sort of have two different stories to leave you with then. In the glass half full scenario, I would say that coastal exposure is not increasing quite as fast as we thought it was, because we haven't really been properly accounting for the protection offered by persistent shore fast ice in the late spring. So that's glass half full. The coastal exposure is not as bad as we thought it was. Here's the glass half empty. We're still seeing a lot of erosion, and the North Slope has some of the highest erosion rates globally anywhere. And that result is happening with even less forcing than we thought there was. So if the forcing did get as bad as we thought and as bad as we might forecast it to be, then we can expect things to just accelerate. And I'm sorry to leave you with that message, but I think it's the honest one, that if the shorefast ice starts to really go away and doesn't provide that sort of late spring, early summer protection, then the coastal change may really accelerate. All right, with that, I'll take questions.
All right, well, thank you, all three speakers. We will take, I see Charlie, and I know I've got some questions too. Before we get to Charlie, I just want to let everyone know that while we're all enjoying this talk, all these nice people, some of them are in different time zones. Harper's in Alaska, but everyone else is on different time zones. A little love in the chat box for taking the time to talk to us up here. So while we're going through the questions, the speakers always appreciate it. And that's good. With Charlie, you are quick on your square. Go for it. Unmute yourself. Or I can.
This is Charlie.
Go for it, Charlie.
Yeah. So here at Nome, we have longshore marine transport, and there's a lot of sand being moved from 5 meters to 0 meters in the coastal environment, but you get out much beyond 5 meters and there's a lot less alongshore transport going on. And I just thought that might, on the North Slope, have quite the effect. I know there's a lot of coastal lagoons and sand spits and so forth, and so I imagine they have something similar going on there. There's a comment for Jim.
Yeah, thanks, Charlie. That's a pretty common phenomenon worldwide, actually. We call that sort of 5 meter number, or it varies from location to location, but we often call it the closure depth. And what we mean by that is the depth at which things don't really change very much anymore. But at depths shallower than that, then the system is really responsive to even an individual storm or multiple storms, or at depths shallower than that, that's where things change a lot in the winter. And then they change again in the summer because they're really responding to seasonal signals. But deeper than that, it's not as extreme. And that's really about the waves. You know, the surf zone where the waves break and the motion gets really violent and turbulent, that's usually shallower than 5 meters. And that depends on conditions, depends on, you know, whether there's sandbars and all that stuff. But the real shallows, that's where the wave action gets really vigorous. And that's where you pick sediment up and move it around. And you have stronger currents there and all those things. So I'm not very surprised to hear you say that number. I do think that over longer kind of decades, kind of timescales, that closure depth might stay the same. That number, 5 meters, might stay the same, but its location might move because the whole shoreline, is retreating. And when it tends to retreat, there's a suggestion that it does so in a self-similar way. What I mean by that is it keeps its shape and it just marches that shape, towards the land. And so it would, on a seasonal time scale, it would still have some closure depth that doesn't change much, but on over the course of decades, it keeps moving. So anyway, your point's well taken. I agree, and I'm not really surprised to hear that. And I think it's sort of a question of what time scale of change are we talking about? Are we talking about this season, that season, next year? Are we talking about 50 years?
Thanks.
So it sounds like there may be audio problem at this end, but if you can't hear me, let me know.
Oh, you sound better now, Gay.
I sound better. Okay.
Yeah.
It's a brand new laptop, and it's been just a nightmare. But anyway, so we also have a question from Rick Toman, or Dean, are you back? Is this a second go?
Second go.
Okay, and then Rick.
So first of all, thank you for mentioning permafrost melting. I think that's very important. With permafrost melting, your erosion and heating waters, that's very important to the phytoplankton off the coast. I'm a phytoplankton person, so the physics helps a lot, but all of that potentially can impact harmful algal blooms off the north slope. So I think you have some very important information to give to the biologists. The second thing is, I didn't hear you talking anything about winds with like upwelling, downwelling off the coast. Is it constant? Is it changing? Can you incorporate that into your nearshore ice problems?
Boy, that's a great question. I did not mention winds at all. In some ways, by accounting for the waves, we account for some of the wind effects because the waves integrate the wind and they're kind of the net result of the wind. But the wind does move the ice on its own, absolutely, and then it causes upwelling and downwelling. And one of the really remarkable things in these year-long time series of these observations we have at every one of these sites is how much the water levels really change. And it's definitely all coastal upwelling and downwelling and set up and set down. And on the kind of scales of weeks, we get these 2 meter changes in the water levels, and that really that controls where the inundation will be at the coast, right? When and if there's a storm that coincides with one of these high water level times because there's strong upwelling, I mean, man, it's just it's bringing the water that much further up, and it has a big difference. So it is definitely another factor to include. We haven't found such a clear signal to adjust these reanalysis products with these global products with as that one, but it's something. One of the things I would really like to do in the future, like my next big project that I would love to do in this region, is to try to really understand the shorefest breakout events and try to understand it on the event scale. The shorefest ice has been there all season, and it's grounded out to here, and it's got this much compaction, and this is what the stress and strain is within the ice. And then when it finally leaves, did it leave because warm water came in? Did it leave because the sun has been shining for 2 weeks? Did it leave because some waves came in? Did it leave because the winds were blowing? And it's going to be different every year for every event, but I would like to have a better overall understanding at a fundamental level of when and why the breakout events occur, so that we can predict them in the future, and then we can include them in the forecast models also.
Yeah, thank you much. Appreciate it.
Rick, I see your hand up, but I do notice we have some participants from the Bering Strait region that are listening in that are not from Nome and are in one of the more remote communities that oftentimes loses internet. So I'm just going to stop for a sec and make sure that anybody who is tuned in from afar or one of the islands, if you have a question, you should ask and come to the front of the line, because I know that I am amazed that you guys are having a connection all the way through this. So it's awesome that you joined via Zoom. If there's any question, feel free to jump in and we'll hold, because I like to give priority to communities that are right outside the region. I mean, right outside of Nome. And until we hear from them, maybe Rick, go ahead.
Yeah, thanks, Jim. I didn't mean to throw up a roadblock there with the ERA 5. I do think that it's a great opportunity. So ERA 5 at a 1/4 degree resolution, still can't resolve this, and it's a great research opportunity. Okay, what do we need to do to get that to where we can start to resolve what's going on in the immediate near shore there? So it sounds like a great master's or PhD project there to downscale that to, and it sounds like that might potentially dovetail with your interests on, okay, what's physically going on with the shore fast ice breakout. So thanks.
Yeah, I absolutely agree. It is kind of another part of that project has been to run these fine scale models that are nested within those kind of models. And so you use something like ERA5 or these large scale models as the forcing, and then you have something that's much more refined that you run there. One of the biggest problems we have with all of that is having good information to get started, the initialization, the initial conditions, good information on the ice in particular. You know, I mean, the satellite era has given us so much information about ice, and yet it still misses so much. You know, a lot of those products are once a day, and they don't really have very fine scale resolution. They have no idea how thick the ice is. They just say, oh, there's ice there and there's not ice there, right? And I'll tell you how strong the ice is. They don't, you know, none of the things that you would measure if you could actually put your boots on the ice, if you could drill a hole in the ice, if you could go out, right? You don't get that. And so sometimes these models have a garbage in, garbage out problem. If you don't feed them good ice information, the result you get out is going to be junk.
Yeah,
So
absolutely.
Jim,
Thanks.
thanks, Rick. And Jim, just a comment. I mean, to know the quality, types of ice, thickness of ice on a real-time real-time close scale, high resolution. This coastline from all of Western Alaska and Northern Alaska is inundated with people who are incredibly knowledgeable on that level. Is that something in the future when you go forward with looking at that? Would you be interested in working closely with communities who could provide you a level of expertise that is beyond for regional, you know, the satellite gives you the whole big, beautiful view, but near shore, you're talking shore fast ice.
Yeah, I would love to do that. And I think, you know, there's already a lot of nice initiatives underway, right? The AOK, the Arctic Alaska Coastal Observing Network, and then there's the new, you know, community engagement thing that just started up. And I think that would be great. And I think it's for me, these things are most fun when you have a real targeted goal, right? I mean, I love just sitting down and talking and you know, hearing stories with everyone, but it's even more fun when you've got something like we want to understand this, you know, we want that happening. So I would love to do that.
And I know
there is
you
a
guys
question
are,
from Raphael on the chat. If you
okay, yes. And also, before we get to Rafaela's question, I do want to just go, and Rick is also, because you guys were enamored with, and rightfully so, we all are in the Bering Strait region with those satellite images he's able to provide to us. He provides them on a Facebook page as well. Then he lists the name, it's Bering Strait Region and Climate Weather. And so if I highly recommend you guys ask Rick to be invited to his group, just go and like it and you'll get a little invite. Anybody in this that's listening in. And magnificent, and it's for this region, it's pretty epic that anyone spends time focused on the Bering Strait. So we are the center of the universe here, and so it's a great place to get some fantastic imagery and information from Rick and all his magical things he has at his fingertips. And for Rafaela, how well do you think the seawalls are going to work to control erosion? Faro Utkiagvik is thinking about one, or at least is in the discussion.
Yeah, they're in the discussion with the Army Corps, right? I mean, they have some cost estimates, and they're big, and they want to save Steveston Road, and I think those are all worthy goals. Let me try to give a more big picture perspective, and maybe not comment too much about that project because I don't know enough about that project, but I do teach coastal engineering, and I know I talk to a lot of people in practice right now that there has been a dramatic shift in the last few decades in terms of whether coastal engineering solutions are seawalls and breakwaters and what we call hard solutions, big things that you build that stop the water and hold the line and say, well, here's the shoreline and the shoreline's going to stay here. there has been a real shift in the discipline to do soft solutions instead, which are to restore coastlines to their natural shapes and their natural equilibrium, restore habitats for all the things that live there, and to not try to hold the line like that anymore. And coincident with that, there's a practice that's ongoing that's called managed retreat, where you take some of that infrastructure and move it backwards. That is very fraught and very politically just difficult. I think there are a lot of justice issues that have come up with that have not been well handled. A lot of that, the idea of retreat is based on property values, and then the efforts to retreat are only helping areas that already have high property values, and it's basically it ends up being a program to help wealthy communities, and it is of no use to the rest. So I'm not really advocating for managed retreat in the way it exists right now, but I think that some of these other concepts are in general things that are important to put on the table when you talk about, what are we going to do about a particular stretch of coastline where the road is washing away? Do we build a big wall and hold the line, or do we figure out other solutions that are basically in the long term going to be more adaptable, right? Because the thing about a seawall is that eventually it will fail, or eventually it will need very expensive repair. It can be a great solution for a decade or more, but the clock is ticking as soon as you build it. So, when you've done that, you have to sort of have a plan for what happens after. Whereas some of the newer, ways of engineering practice are these solutions that try to take cues from nature and get the system closer to what it's doing. And if the coastline is in retreat anyway, let's do something that's going to retreat in a way that is manageable, right? That we know this equilibrium profile and this closure depth, they're going to kind of keep slowly marching backwards, and we have some idea of what that rate is. And so we know, let's take the critical infrastructure and let's move it, 50 years back or 100 years back. And then we'll let that, that means that critical infrastructure is not right at the coast anymore. So you don't have a shore road anymore. And maybe there are problems with that. I understand that there may be stakeholders who really need that road. But on the other hand, now you've restored that zone, and that might have a whole bunch of other benefits, some of which haven't been occurred. Anyway, so these are difficult decisions because there's a lot of technical stuff that goes into it, and there's also a lot of stakeholder engagement, a lot of political and some justice issues that come in. So it's a hard one to weigh in on just unilaterally. But I will say that seawalls are generally falling out of practice for a number of reasons that are quite real.
Thank you, Jim. And Rafaela says, thank you very much. So you answered her question. And Rick, your hand is still up. Do you have another question? Maybe.
No, I just forgot to lower it.
Oh, okay. I can do that too. I just noticed. Dean, I've got one question. Then then you go. My question is, so here's what we've got the melt. This is like a Bering Strait version of what I think you just gave us, is that you've got the ocean is melting, and the hot water's coming up from the south to the north, and it's going into Chukchi, Beaufort at a pretty good clip. We know that from here, and it's warm, and it's got fresh water from the ice. Is that right? Why it's getting pinched, and it's going down. This nice, warm, salty water is going down, and it's going to eventually pop up under the ice. Is this a new event, or is it because the last couple of years, meaning the last 20 years, have been aggressively, for us, warming? Has this been always the function, and we're just sort of thinking about it now, or is this because we've had 20 years of hot, boom, and then the last, 2015 on up, it's just been, 2017, 2018, 2019. Those were extraordinary years for the Bering Strait Reef, for the northern Bering Sea. And so is this thing that you're seeing, is this new, or has this kind of always been, but just it's just been weaker in the past? And then eventually when we just keep, their forecast is like, we're going to just keep sending this to you more because it's happening to us more here in the Bering Strait region. So I guess that's my question. Is this kind of new, or is it new just because the strength of it has changed or not. I don't know.
Well, I can answer that one. Maybe I think or tried the. I think this process of the water coming through Bering Strait region and then ducking underneath the, getting squeezed underneath the surface water is not new, but the water that's doing that is getting warmer and warmer and warmer. So
Okay.
it used to be 1 or 2 degree water above freezing, and now it's 6. And so it's just warming up. Same process, warmer water. But
Warmer water.
we've been part of the thing that we were excited about with our stuff is that it's the process, whether it's with 1 degree water or 6 degree water, it's not included in forecasts right now of sea ice melt because we didn't really understand how it worked. And so we were excited to kind of figure out a little bit how it works so that we can add it to forecast models.
Awesome. All right, thank you. And Dean, if you can hold off, I just saw Marina, Marina, we're trying to get on, of course I was blabbing, trying to get a question in, and I don't know if they were able to stay on. I think we lost them.
Hi. Can you hear me?
Oh, no, you're there. Go ahead, Jared. Go ahead, Jared.
Hey, I got a question. Where does 2 meter come from? How do they measure the ocean? The 2 meter.
The
2 meter, the
the
depth
wave-
of the ocean or the ice
Yeah,
or?
the depth of the ocean, the rise. I mean, the rise of the
Oh,
ocean.
2 meters
How
per
do
year.
they
Ah,
measure the 2
yeah.
meters?
So I should clarify that, Jared. It's not the ocean sea level rise is not 2 meters per year. It's not a vertical measure. It is a horizontal one. It's that the shoreline is going backwards 2 meters per year. And the way they measure that is they take aerial photos and they look down and they say, okay, we'll reference it to a survey point and say the shoreline was here last year. And then this next year it moved backwards 2 meters, but it's a horizontal movement. Like it's going in the North Slope, the shoreline's going southward 2 meters per year. And they're using aerial photography to get that. Does that make sense?
And that 2 meters is just for the North Slope Borough, just for the North Slope Borough beaches, or were you talking about us too down here?
I don't know the
Well,
number
us
for
too.
Nome.
Go ahead, Jared.
Yeah, I was talking about us, but if it's North Slope Borough, it's probably a different story.
Yeah.
I'll look into it. I don't know the number for the Nome region. It's a different database. The USGS is doing that work, and they separate it by region. And I haven't looked at the Nome numbers in a while, but
We're
wouldn't be
having
surprised.
phenomenal erosion issues. Because we're less ice, even
Right.
more so lately. We're like what
Okay,
the
thank
North
you.
Slope
That's
Borough will
what I
look like.
wanted to ask.
Thanks, Jared.
Thank you.
All right, we've got Dean and Rick. Dean,
So
why don't you go ahead?
Okay, so I know most of your work is focused on the heat coming up into the Beaufort and into the Canada Basin, but a lot of that does turn the corner. Is there any evidence of an increased heat transfer through the transpolar drift? And I know that may be out of your scope, but anything would help.
Harper, do you have any thoughts?
I have no idea.
Fair enough, fair enough. No problems.
Gotcha.
All
Good
right,
to have
good
honest
question,
answers.
Dean. Good question, Dean. And Rick, your hand is still up, so I'm guessing you do have another question. Nope. I'll ask mine. And then, are you guys okay answering all these questions? We're kind of gone over the mark.
Oh,
we're-
can you hear me?
Go ahead, Rick.
I just wanted to thank the authors for their provocative title. of Bering Sea heat bombs. Everyone on this webinar knows that what goes on in the ocean is important to what happens with Arctic sea ice, but that gets lost in the media a lot. And so having a nice provocative title like that helps ram home that, and it makes, for those of us that do climate science communications, that helps us to help the media make the connection. It's not just about air temperature. What happens in the water is important too. So thank you.
Thank you, Rick. You guys all right with questions? If you can take a few more.
Sure.
All right. So my question is, you had the chlorophyll was low in the little pinched off hot water bits, and but the organic matter was high. And I guess you can't figure out what is in those, but you had a little thing with copepods, and I didn't know if that was just a schematic or a real thing. But is this in any way, we've been seeing some differences with bowhead migration and some of the other animals that would be eating copepods and organic matter, if that's meaning zooplankton in general. Is this something that, anybody looking at the patterns of this, these heat pinched off pools of water and what we're seeing with some of the animal movements for animals that would be preying on what may be in those? Chlorophyll being down was kind of interesting to me because I'm a little confused by that, but the zooplankton, or the organic matter, if that's what you're calling it, is high, then animals may target that because it's concentrated, and it would be easy to find out a temperature difference and go in for that, or a density difference and go in for that.
That is an excellent question. And we were surprised by the chlorophyll as well. I think our conclusion in the end, by looking at all the different bits, was that this water, which is coming off the shelf, is somewhat nutrient depleted. So they've run out of food. It's a whole bunch of, critters, and they've kind of used up their food over the months in the summer. And so their population is starting to decline because they've eaten, or they've used all the nutrients there are. And so they get spat off. But then as these little bombs go into the Arctic, there's still some populations in there, all that organic matter, and suddenly those little warm patches are interspersed with all the nutrient rich cold water. And so that as they're stirred together and mixed, that can facilitate a next bloom of them potentially. But I almost wonder if one of our audience members, Seth, would like to comment on that.
Seth, you're being called out.
Not to
got an answer?
Put you on the spot.
Hey there. I'm not sure I can shed too much light on all this, but I think that the CDOM measurement, the color dissolved organic matter, is not so much actual zooplankton gay as it would be like the tannins and dissolved organics in the water there.
Okay. Helpful. I was going with the schematic. I saw all these little krill, and I'm like, oh.
Yeah, that was artistic license of the
okay.
Video people.
So I'll step in and I'll back up what Jennifer was saying. Typically during that time of year, you get a drawdown of the nutrients in the surface waters. Then you get a subsurface chlorophyll max that's sitting on that density layer. That cold water underneath is still fairly nutrient rich because light only goes so deep, and photosynthesis starts to wane down at those deeper depths. I think what we saw in your profiles was an actual deepening of what I would call the chlorophyll max, just because you had that warmer water over it that was already nutrient deplete. And I agree with Seth that the CDOM values are something probably more terrigenous or old decaying blooms. So I think you're right in your evaluation, Jennifer.
I'd also maybe follow up on that, Dean, and say that this CDOM signal is one of the things that ties Jim's work together with these blobs and their observations. We had a student who graduated a year or two ago who was looking at the terrestrial derived organic matter in the bacteria and the communities in the sediments in the Chukchi Sea. And I was kind of surprised that she found that a large fraction of the organic matter there was terrestrial in nature. It was not organic matter coming north through Bering Strait of the Anadyr water flavor. It was not oceanic in origin. It was actually terrestrial in origin. And as the permafrost thaw accelerates and erosion accelerates, there's just so much organic matter in that eroding shoreline that's then getting brought out. And the question of where that organic matter goes and what role it plays both in the ecosystem and in the climate system, those are some of the questions that are super interesting still.
And high water, river runoff too.
One of the things I know,
the lignins that are being brought out of the permafrost are long-term, slow decomposing elements that would be high CDOM values. So yes, you're right. Those are terrestrial origin. They're probably lignins of some sort, some vascular plants that are coming from, as Gay mentioned, from river runoff. And they'll sit in the sediments for a long time. And if they're re-stirred, if they're redistributed up into the water column, you're going to get a CDOM signal that's terrestrial. So yes, I think you're both right there.
One of the things that I think I've heard other people talk about that seems really interesting is that you have this different type of terrestrial runoff and different things, but then actually as the water gets warmer, that might make for ideal environment for slightly different species, kind of from the microbial level on up, than was true with colder water, just because the ideal conditions vary. And so, you have different compositions of picoplankton versus bigger, and how those like really small, very basic ecosystem stuff changes seems like a real interesting question.
All right, well, thank you. And I guess we better let you guys go.